In today's lecture, we shall consider another predictor corrector pair, which is a multi-step method. This method is called Milne's predictor corrector method. This is again a multi-step method where we assume that the solution to the initial value problem dy by dx equal to f of x comma y is known at a set of previous equally spaced points. Namely, the solution is known at x0, x1, x2, x3, and you are asked to get the solution at the point x4. Information about the values y0, y1, y2, y3 are known to you, and you are asked to get the solution at the point x4, namely what is y4. So, under this assumption we develop Milne's multi-step method and also derive another multi-step method, and we will see how these two multi-step methods can be considered as a predictor corrector pair for computing solution at the point x4, namely y4. So, we integrate dy by dx equal to f of x comma y with respect to x between x0 and x4. So, integral x0 to x4 f of x comma y dx. So, this gives you y between x0 and x4. So, y4 minus y0 is integral x0 to x4 f of xy dx. We approximate f of x comma y by Newton's forward interpolation polynomial. It is f0 plus p into delta f0 plus p minus 1 by factorial 2 into del square f0 plus p minus 1 p minus 2 by factorial 3 into del cubed f0 p into p minus 1 into p minus 2 into p minus 3 by factorial 4 into del to the power of 4 f0 and so on, and this must be integrated with respect to x. And what is p here? P is x minus x0 divided by h, where h is the step size such that xi is x0 plus ih. So, I takes values 0, 1, 2, 3 up to 4. So, we now make use of this information and change the limits of integration from x0 to x4 accordingly. So, dx will be h into dp, and when x is equal to x0, p is 0, and when x is equal to x4, p is x4 minus x0 by h. So, it is 4h by h. So, it is 0 to 4, and since dx is h dp, so this will be h, and you have f0 plus p delta f0 plus p minus 1 by factorial 2 into del square f0 plus the remaining terms as they are. Into del power 4 f0 plus etc. Now, integration, as I said, is with respect to p. So, it is dp. We have to evaluate this integral and then substitute for the forward differences delta f0, del square f0, del cubed f0 and del power 4 f0 and simplify this result. So, when we perform integration, we end up with the following step. I have already indicated how you do it when we considered Adam-Moulton method. So, I just give the results of the integration of this step. So, it gives you y4 equal to y naught plus h into 4 f naught plus 8 delta f naught plus 20 by 3 into del square f naught plus 8 by 3 into del cubed f naught plus 28 by 90 into del power 4 f naught, and we consider terms up to this. And since delta f naught is f1 minus f naught, del square f naught is f2 minus 2f1 plus f naught, del cubed f naught is f3 minus 3f2 plus 3f1 then minus f naught. We substitute these forward differences in the terms which appear within the bracket and simplify, and we end up with y4 as y naught plus 4h by 3 into 2f1 minus f2 plus 2f3 plus 28 by 90 h into del power 4 f naught. So, as before, this term gives you the local truncation error. So, our method is that y4, the value of y at x4 depends on y naught and then y1, y2, y3, because what is f1? f1 is f at x1, y1, and that is from the differential equation y dashed. So, y dashed evaluated at x1, y1. So, it is y dashed 1. Similarly, f2 will be f at x2, y2, and so it is y dashed at x2, and f3 is f at x3, y3, and that will be y dashed at 3. So, the solution at x4 given by y4 depends on the solution at the previous points, namely x0, x0, x1, x2 and x3, and that is why we assume that we already have some information about the solution at the previous 4 points. Suppose say this information is not given and your problem is something like this: dy by dx is equal to f of x comma y, and y at x naught is y naught, and you are asked to say get the solution at some point a, y at a is what is required, and you are asked to solve this by Milne's predictor corrector method. We will derive the method, but I am just indicating here because we said that this method is based on the assumption that solution at the previous 4 points are known to us. Here we are only given information at the point x naught. So, what you do is you divide this interval a to x naught into say intervals such that you have points x1, x2, x3 and x4 is going to be your a. So, divide the interval of width a minus x naught into 4 equal parts by means of points x naught, x1, x2, x3 and x4, which is a. So, information at this point is given by the initial condition. At these 3 points you require the information if you want to make use of Milne's method, namely the predictor method or the multi-step method that we have derived here. So, what you do is you make use of either Runge-Kutta method of order 4 or Euler's method or Taylor series method, march from x0 to x1, obtain the solution by any one of those techniques and get the information here, call it as y1, and do that for each of these points, namely you march from x1 to the point x2, use any of those methods that we have discussed, namely Runge-Kutta method or Euler's method or Taylor series method, and compute the solution at x2, which is y2, and by the same technique march to x3 and then come and determine the solution at the point x3 and call it as y3. So, now you have information at the previous 4 equally spaced points. So, you must take the points in such a way that you divide the width of this interval x0 to a into 4 equal parts of step size equal to h, and then march from one point to another point and determine the solution at each of these previous points. Once you have the information at all the 4 points, computation of the solution at A, which you call as x4, namely y4, can be obtained from the multi-step method that you have derived. So, either you are given information at the previous 4 equally spaced points. If it is not available, then you divide the given interval into 4 equal parts of step size h, and then use any of the single step methods to compute the solution at the previously located equally spaced points. And once you have this information, you make use of the multi-step method that we have derived now to get the solution at x4, which is y4. So, we now derive another multi-step method. To do that, we integrate dy by dx is equal to f of x comma y with respect to x between say x0 and x2, x0 and x2, and this will give you y between x0 and x2. So, it is y2 minus y0, and that is equal to integral x0 to x2 f of x comma y dx. So, you approximate f of x comma y by again Newton's forward interpolation polynomial, namely f0 plus p into delta f0 plus p into p minus 1 by factorial 2 into del square f0, p minus 1 into p minus 2 by factorial 3 into del cubed f0 plus etc., and integrate it with respect to x. Here again p is x minus x0 divided by h. So, making use of this, you can change the variable of integration, namely with respect to x can be now changed to integration with respect to p. So, when x is x0, p is 0. When x is equal to x2, p is x2 minus x0 by h, which is 2h by h, and that gives you 2, right, and that the terms within this bracket will have to be integrated with respect to p. So, dx is h dp. So, you integrate with respect to p between the limits p equal to 0 to 2. So, the result of integration and then replacing the forward differences by means of the values of the function at x0, y0, x1, y1 and so on will result in the following method, namely y2 is equal to y0 plus h by 3 into f0 plus 4f1 plus f2 minus 1 by 90 times h into del to the power of 4 f0. So, you have another method. We observe at this stage that we have y2 to be given by y naught plus h by 3 f naught plus 4 f1 plus f2, where f2 is f of x2 y2. So, this requires knowledge of y2, so that f can be computed and that can be made use of here. But what is the value of y2 is the question. This suggests that the value of y2 that we have here can be obtained from the multi-step method that we have derived earlier. So, we can call that as a predictor and use that value over here, so that f can be evaluated, and using that information the new value of y2 can be obtained. So, that this can be called as a corrected value. So, let us now properly denote the nodes and write down in general what the two methods are. Say in the first method, I am required to compute the solution, say at xn plus 1, which is yn plus 1. I require knowledge of the solution at the previous 4 points. So, I shall call those 4 points as xn, xn minus 1, xn minus 2 and xn minus 3, where the values are yn minus 3, yn minus 2, yn minus 1 and yn. So, the predictor that we have obtained can now be written as yn plus 1, which we want to predict, clear, is y naught. Just look at this picture, right. y4, which has to be predicted, is given by y naught, which is the solution at x naught. So, if I want to put this in general and want the value of yn plus 1 at xn plus 1, then yn plus 1 predicted is yn minus 3 plus 4h by 3 multiplied by twice. What do I have here? f1, that is f at x1 y1. So, generalizing, this is going to be f at xn minus 2 yn minus 2, which I call as fn minus 2. Then I have minus f2, namely it is the value of f at x2 y2. So, correspondingly this is going to be minus f at n minus 1. And then I have twice f3, namely the value of the function at x3 y3. So, in this case it is going to be plus twice fn, and the local truncation error is 28 by 90 into h into del to the 4 fn. So, we have a predictor which predicts the value at xn plus 1, which is given by yn plus 1, and it makes use of the information at the previous 4 points. It is this predicted value which I have to use in the other method which we have derived, and then correct it, so that we can call the other method as a corrector method. So, let us see here. What does this formula tell us? If you want the solution at x2, namely y2, the previous equally spaced points are x1 and then x0, at which the solutions are y1, y0. So, the method gives you the solution at this point. Now, if I want to make use of this as a corrector and get the solution at this point, I call this point as xn plus 1, at which I want to get yn plus 1. So, the previous point will be xn and the one before that is going to be x n minus 1. If I want to generalize this to a result involving these 3 points, then the method tells me y n plus 1 is equal to y naught, which corresponds to the solution y n minus 1, then plus h by 3 into f naught, which is the solution here. So, it is going to be f of x n minus 1 y n minus 1. So, I call it f n minus 1. Then plus 4 times f 1, corresponding to that here it is going to be f at x n y n, which I denote by f n. And then I have f 2, namely the solution at this point, and corresponding to that I should write down the solution at the point f n plus 1 minus 1 by 90 h into delta to the 4 of f n minus 1, which is the local truncation error. So, I have the method written in general in terms of x n minus 1, x n and x n plus 1 and the function values there. So, as before I observe that this f n plus 1 is f of x n plus 1 y n plus 1. So, I require information about y n plus 1. Where do I get it from? I get that information from this predicted value. So, I call this f n plus 1 as being obtained from the predicted value, or as being obtained by using the predicted value of y n plus 1 from that method. So, I compute f n plus 1, call it f n plus 1 predicted. So, I know every term on the right hand side. So, I get the value of y n plus 1. Since I have obtained a new value of y n plus 1, I call this y n plus 1 corrected value. So, I predicted it by using formula A and I corrected it using formula. At this stage, I check whether the absolute value of the difference between the corrected and the predicted values of y n plus 1 is less than epsilon. If that happens, then we stop our computations. If this does not happen, then what do? I make use of this method once again and get the second corrected value, where I make use of the y n plus 1 first corrected value in computing f n plus 1. So, I shall denote this by f n plus 1 corrected value, and hence I get the second corrected value. And once again I check if the second corrected value minus the first corrected value are such that the absolute value of the difference between them is less than the desired accuracy. If so, we stop. If not, we recorrect this again using this multi-step method. So, this method which we have derived is a corrector method, whereas the one which we derived earlier is a predictor method. So, we make use of A and B as a predictor corrector pair in obtaining solution to dy by dx is equal to f of x comma y, when information about the solution is known at the previous 4 points which are equally spaced. And this method is called Milne's predictor corrector method. Let us now consider the following example and solve it using Milne's predictor corrector method. Find y at 2.0, if y of x is the solution of dy by dx equal to half of x plus y. Given that y of 0 is 2, y at 0.5 is 2.636, y at 1 is 3.595 and y at 1.5 is 4.968. So, we are asked to solve this problem using Milne's predictor corrector method, and we are required to get the solution at 2, and we are given information at 1.5, 1.5 and 0. So, we have information at previously located equally spaced points, which we call as xn, xn minus 1, xn minus 2, xn minus 3, and the solution is required at xn plus 1, namely yn plus 1 is required. So, we use the predictor given by yn plus 1 predictor is yn minus 3 plus 4h by 3 into twice fn minus 2 minus fn minus 1 plus twice fn. What is yn minus 3? Yn minus 3 is the solution at 0. So, it is y naught which is required, and y naught is given to be 2. So, it is 2 plus 4 into what is h? The points are equally spaced and the step size is 0.5. So, 4 into 0.5 by 3 into twice f at n minus 2. So, let us look at xn minus 2. So, it is 0.5 and information at 0.5 is that it is 2.636. Then you have minus f at n minus 1. Xn minus 1 is 1. So, 1, and at xn minus 1 the solution is 3.595, and then we have plus twice fn, that is f of xn yn, and xn is 1.5 and the solution yn is given to be 4.968. So, it is always better to write down each step systematically, so that you know you evaluate your function at these points xi, yi, and then use the differential equation. What does it say? It says f of x comma y is half of x plus y. So, f of 0.5 comma 2.636 will be half of 0.5 plus 2.636. So, similarly, you can evaluate each of these functions which appear here, and if you simplify that, you end up with the predicted value as 6.8710. So, this is a predicted value, namely this is the value of y at xn plus 1, which is 2. So, yn plus 1 predicted is y evaluated at 2, and that is 6.8710. But we need to solve the problem using Milne's predictor corrector method. So, we have a way to correct this solution. How do we do it? We use the corrector method which we have derived. what does the corrector say? It says, if you want to correct the solution at xn plus 1, namely yn plus 1, then the corrected value is yn minus 1 plus h by 3 into fn minus 1 plus 4 fn plus fn plus 1 corrected value. No, correct, yeah, fn plus 1 predicted value. So, make use of this corrector and then get the solution. What is this fn plus 1 predicted value? That is f of xn plus 1 yn plus 1 predicted. So, that is f at, what is xn plus 1? 2. What is yn plus 1 predicted? We just now computed it, which is 6.8710. So, evaluate this. What is f of x comma y? It is half of x plus y. So, that is half of 2 plus 6.8710, and that is equal to 4.4355. That is the only value that you need to compute. The other values fn, fn minus 1 are already available to you because you have used them here. So, those values are available to you and you can take from there and substitute these by the values that you already have. And so, the corrected value of yn plus 1 is y at 2 corrected, and that is equal to y n minus 1. So, when you use this method, you have to again mark those points xn plus 1, xn and xn minus 1. The method says the value of y to be corrected here is based on the value of y here, which is yn minus 1, and the function value f of xn minus 1 yn minus 1 plus the function value here, namely xn yn. So, if this point is 2, then xn will be 1.5, xn minus 1 will be 1. So, mark clearly what the points are and what the function values are. That is very important. And when you substitute those values, so can you tell me what is yn minus 1? It is the value of y at xn minus 1, namely it is the value of y at xn minus 1, which is 1. So, y at 1, which is 3.595, then plus h, that is 0.5 by 3 into what is fn minus 1? It is f of 1 comma yn minus 1, that is 3.595, namely the value that you have obtained here. So, that turns out to be 2.2975, and then 4 times fn, namely f at 1.5 comma 4.968, which turns out to be 3.234, and finally fn plus 1 predicted that you already have computed. So, 4.4355. So, simplify this and that gives you 6.8731667. So, this is the corrected value of y at 2. So, let us try to apply this corrector again and recorrect the solution and see how it can be done. Before doing that, what is the formula that we have to use? We write down the formula. So, yn plus 1 second corrected value is yn minus 1 plus h by 3 into fn minus 1 plus 4 fn plus fn plus 1. Now, here this Fn plus 1 is corrected using the information Yn plus 1 corrected. So, Fn plus 1 is f at xn plus 1 comma Yn plus 1 corrected. Yn plus 1 corrected has been obtained and xn plus 1 is 2. So, we can now compute what is Fn plus 1 corrected value. So, it is f of xn plus 1 Yn plus 1 first corrected value, namely it is f of 2 and the first corrected value is 6.8731667 and that is half of 2 plus 6.8731667. So, that will give you 3.595 plus 0.5 by 3 into 2.2975 plus 4 into 3.234 plus the value which you have got here. What is it? It is 1 plus 3.436583335 and so that will be 1 plus 3 point. So, 4.43658335. So, when you simplify this, you get the solution as 6.8733467. Suppose say I have asked you to perform 2 iterations or correct the predicted value twice, then it is enough that you stop your computations at this step because you have performed the correction twice. On the other hand, if suppose you are specified some accuracy, then you will have to check whether the absolute value of the difference between successive iterations turn out to be less than the prescribed tolerance, and if so you stop, otherwise you recorrect your solution till the desired degree of accuracy is attained. So, since I have said in this case stop your computations after 2 corrections, you can write down the solution to the problem as y at point 2 is 6.8733467. So, you have used Milne's predictor corrector method to obtain solution to this problem when you are given information at the previously equispaced points. So far we have considered 3 predictor corrector methods, namely modified Euler's method turned out to be a predictor corrector method, and then we derived Adam Moulton or Adam Bashforth's method, which is again a predictor corrector method, but this method is a multi-step method, and in this class we have derived Milne's predictor corrector method. So, we have derived 2 multi-step methods and we make use of these 2 multi-step methods as predictor corrector pair and then try to obtain solution to a first order differential equation correct to the desired degree of accuracy. So, in the next class we move on to problems which are boundary value problems. All along we have been discussing problems which are called initial value problems, where we have tried to obtain solution to dy by dx is equal to f of x comma y and some initial condition, namely at a point x naught the solution is specified or it is known as say y naught. This problem or this class of problems is called initial value problems. Given this information at x naught, we are asked to get the solution at some point xn, and we have developed some single step methods. We have also developed multi-step methods, and we have used them as predictor corrector pairs, and we have been able to obtain solutions to initial value problems. We now move on to what are referred to as boundary value problems. So, in the next class we understand what we mean by boundary value problems and develop numerical methods by means of which such boundary value problems can be solved. We focus our attention only on linear boundary value problems in this course. The solution of nonlinear boundary value problems is beyond the scope of this course, and you will be doing it at a higher level. So, we consider boundary value problems, namely linear boundary value problems, and develop numerical techniques in the next class.